Hey Dean, how's it going? And hello everyone else who either will join us or watch this on the replay. My name is Shane. I am an Oakland AP Stats teacher. This is year 4 for me, teaching AP Statistics. It's my favorite subject in high school when I was a student. It's my favorite subject now. Super excited to be walking you through AP Stats this year. I'll be coming to you live every Thursday at 8 p.m. Pacific Standard Time. So it's 8 p.m. Eastern Standard Time, 5 p.m. Pacific Standard Time. Every Thursday. You can follow me on Instagram. I haven't posted anything yet. I'm still working out the kinks for that, but I will get that up and running very, very shortly. Today, we're going to talk a little bit about sampling distributions for means. Last week, we talked about sampling distribution for proportions. So just before we get started, Fiveable is now offering Fiveable Plus, which gives you guys access to replays, live stream notes, cram sessions for every single subject on the AP course offerings. So that's $20 before April 1st, $35 after April 1st. So if you do it early, you're going to save more than half on your membership. And it's good till July 1, so you'll have enough time to get all your cram sessions in. Definitely worth it if you are taking more than one AP. Definitely worth it if you are taking only one AP, because it's going to help you get a 5 and save you lots of money on the exam, or in college, I should say. So here's the schedule. Here's the upcoming sessions that we'll do. We're going to start next week with confidence intervals, just the basics, like what is it? Why do we use it? Then we're going to dive into the specific confidence interval. So how do we conduct a confidence interval for proportions? How do we conduct a confidence interval for means? As always, you're going to get exam tips from me, FRQs, multiple choice, the calculator. Dean, do your students use the TI-84 or the Nspire? This is technology that's been going on, gosh, I don't know, 30 years. They don't really update it too much, but they still charge you $100. It's crazy. Some of each. Oh, good for you. You know both. I'm a whiz on the TI-84. The Nspires are a little bit more difficult for me, but I have a book that I can kind of look through if you do need some help with the Nspires. Here's kind of our agenda for the day. We're going to start with just a quick reminder. What's the difference between parameter and statistic? Because those are going to be very, very important when you're writing free response questions on the AP exam. If you write the wrong symbol, they are going to knock you on the AP exam. So it's important that we get our symbols correct on what is a parameter versus what is a statistic. Also going to do a quick reminder on what is a sampling distribution. So we're getting into this sampling distribution. What is it? We need a quick reminder. Then we're going to talk about specifically sampling distributions for sample means, which will allow you to describe the center, spread, and shape. We'll talk about the Central Limit Theorem, which is a really, really important theorem in statistics. And then I have 2 frappies for us to do. One from the second year AP Stats was made 1998, and one from a little bit more recent. It is 2007, I believe. Yep, 2007. So we have one a little bit more recent, which actually was the year I took the exam. All right, let's dive into it. So sampling distribution, again, just what is it and our parameters versus our statistics. So remember, when we have a population, anything that describes a population is going to be a parameter. So that's going to be our mu or our p. So ignore that little p hat. I could have sworn I deleted that. No p hat, just mu and p, where mu is going to represent the average and p is going to represent the proportion. So depending on what you're trying to measure, your parameter could be a mean or a proportion. Now, it is very, very difficult to get parameters from a population, just because usually the parameters we're trying to get are so large. So instead, we take a whole bunch of samples, and samples get us statistics. So I say keep your S's and your P's straight. Samples give us statistics. Populations give us parameters. Just like parameters, statistics, for this class, we're taking averages or proportions. So X bar for averages, P hat for proportions. Again, I want to stress this, and Dean definitely stress this to your students. They need to use the correct symbol on the exam in order to get full credit. So if you're talking about a population parameter and you use X bar, they will knock you down for that. If you're talking about a sample statistic and you use mu or p, they will knock you down for that. So just make sure that you know what you're getting and how to describe it. So earlier I said populations, they're really tough to get parameters from. So instead, we do a bunch of different samples. And from those samples, we create a distribution, which is essentially what we call a sampling distribution. But before we do that, let's take a look at some different questions on what's the difference between a parameter and a statistic. So here I have an example, a 1993 survey conducted by the Richmond Times-Dispatch 1 week before Election Day asked voters which candidate for the state's attorney general they would vote for. 37% of respondents said they would vote for the Democratic candidate. On Election Day, 41 actually voted for the Democratic candidate. So we want to know, what are those numbers in white? What do they represent? Are they statistics or are they samples? So that first one, that 37%. Now that came from the survey of the respondents a couple days before the actual election. So what we're getting here is actually a statistic because it's only from a small proportion. So Dylan, you got those reversed. Yep, no worries. 41% is actually our population, because remember, population are the people that actually voted. So if you voted, that's our whole population, and of that population, 41% went with the Democratic candidate. So actually, our p hat is going to be 0.37, and our p here is going to be 0.41. Again, we really want to make sure we get our language and our symbols correct. So for me, my students, they made a meme of me to remember that statistics have bars and hats. So it's a meme. It says statistics have bars and hats, and then it has like a nose ring for me, and it has a little hat. So if that helps you out, great. But remember, anytime you're describing a statistic, again, from a sample, it's going to have something on the top. Let's try another example. The National Center for Health Statistics report that the mean systolic blood pressure for males between 35 and 44 age is 128, and the standard deviation is 15. The medical director of a large company looks at the medical records of 72 executives in this age group and finds that the mean systolic blood pressure for these executives is 126.07. So again, we have this description. We want to know, what are those numbers in white? What do they represent? And remember, if we're talking about a statistic, or we're talking about a sample, it's a statistic. And in this case, we're talking about average. If it's from a population, we're talking a parameter, which in this case is still an average. So diving into it, hopefully you got this. The average is going to be 128, which is our population average. So that is going to be our mu, or our parameter. Sigma is also describing a population. So it's a parameter. So we use sigma. And then our 126.07 came from only the 72 people that we surveyed, or that we got medical records from. So that's going to be our X bar. That's going to be our statistic. All right, so just a quick review. If you have more questions on it, go ahead and ask the question tab down there, and I can definitely answer that for you. But diving back into our sampling distribution, because essentially from those samples, we take that statistic and we make a distribution from it. So again, a sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the sample. And there's a key part there that a lot of students struggle with, and it's that capitalized part that says all. So in order for you to have a complete sampling distribution, you need to take all possible samples of the same size. Tough to do it when it's a very, very large population. So I broke it down to a population of 3. So if you look at here, my population here is 1, 7, and 10. The population average is 6. The standard deviation is 3.742. In order for me to generate a sampling distribution, I need to choose every possible sample of this population and generate an X bar. So if you look at my first one is 1 and 1, 1 and 7, 1 and 10. and I just keep going until I have all possible samples. That's my sampling distribution. Now, in a large population, that's really tough to get. So we just want to make sure we do it many times. Again, like if I was trying to get the Democratic, like create a sampling distribution from people who are going to vote next election, impossible for me to get every single sample of size 50, let's say. So instead, I just get a lot, and that gives me a sampling distribution. But it's technically not a sampling distribution because I don't have every size or every sample of that size. So I did this activity with my students where we looked at text messages. I had 4 students record their text messages for about 60 days. So they counted how many text messages do I have. Here was our first student, Sally. And up here, you're going to see the population distribution. So you can see it's really normal, and it's very symmetrical. So what they did first is they took samples of size 4, and they did that 20 times. So notice the spread of this. The next time I had them take size 10. Notice the spread decreased. And watch what happens when I had them take a sample of size 30. It got even smaller. We talked a little bit about that last week with proportions. The same is true when it comes to means. If I have a population and I take a sample, the bigger my sample, the smaller the spread of my new distribution. So this down here is my sampling distribution. With my students, I always say sampling distribution, so they know it's a sampling distribution. They are really annoyed with it, but that's okay because they'll remember it on the test. So notice the sampling distribution has a smaller standard deviation. And we can actually calculate that specific standard deviation in a minute. Here's another example. This was Jamal. Notice this is the population. So either he sends a lot of text messages over here, or he doesn't send that many at all. Notice when we only took a sample of size 4, the spread was really big. As we increased our sample size to 30, it got smaller and smaller. And Dean, this might be a great activity for you to do with your students as a review, because I know you've already covered it. So if you want this activity, just in the chat, let me know and I can email it to you. It does take a full block day. It was about a 90-minute class, but students really understood what a sampling distribution was, and they got to physically see how it got smaller and smaller, the spread. Okay, so we talked a little bit about the spread being a specific number. Well, we can actually find that. So if you look here, we have 2 different measures of, well, we have 1 measure of center and 1 measure of spread. So at the top, we have the mean of a sampling distribution of X bar. So you're going to see that the mean of a sampling distribution right here, and again, you really want to make sure you write the notation correctly, mu of sub X bar, is going to equal the true average of the population. This is super important because when we want to make inferences about a population, it's really tough to get a parameter. So instead, we get a bunch of statistics, make a sampling distribution. The center of that sampling distribution will give us the center of the population distribution. So it's pretty straightforward. And again, we'll do a couple examples to help you out. The standard deviation of a sampling distribution of X bars is a little different. It's not the same as the population. It's going to shrink. And it's going to shrink by the square root of your sample size. So whatever your standard deviation of the original was, divide it by the square root of n, your sample size, and you'll get your new standard deviation of your sampling distribution, okay? As long as the 10% condition is satisfied. So this is a little asterisk I like to throw in because students need to know, right? If your sample size, which is small n, is less than or equal to 1/10 of your population, then you're good to go and you can use this standard deviation formula. If that's not the case, then that is not true. That is not accurate for your standard deviation. And I'll show you an example because sometimes it might be a little tricky. And this is true no matter what the shape of the population distribution is, which is really helpful for us when we don't know what the population distribution looks like. So these two things are true regardless of what your population distribution is. So earlier we looked at this, right? This was bimodal, and this was normal. So if I took more and more samples, both would become normal. They would be centered around the average, and they would have a standard deviation of whatever our original standard deviation was divided by the square root of n. Let's go back to our original example where we saw our mu. Notice I used mu here because that represents a population parameter. So that was 6. If we go over to our sampling distribution, our x bar is still 6. So the average of our sampling distribution is the same as the average of our population distribution, or I should say the center, right? Our standard deviation here was 3.742 for our population distribution. If I go over to my sampling distribution, my standard deviation is 3.72, and I divide it by the square root of 2. So I get my new standard deviation, which is 2.646. All right, so very, very important that we use our standard deviation and the square root of n to describe our sampling distribution, the spread. As we increase our sample size, if I change this to, let's say, 5, we're dividing our original standard deviation by a bigger number, which is going to decrease my spread. And that's kind of what the 1998 FRAPI is all about, and I'll show you in a minute. All right, so let's take a look at an example. The customer care manager at a cell phone company keeps track of how long each helpline caller spends on hold before speaking to a customer service representative. He finds that the distribution of wait times for all callers has a mean of 12 and a standard deviation of 5. The distribution is moderately skewed to the right. Suppose the manager takes a random sample of 10 callers and calculates their mean wait time. What would the mean of the sampling distribution be? Okay, so remember, doesn't matter what the shape is of the population. Our average for our sampling distribution, or our center for our sampling distribution, or our mean for our sampling distribution is going to be the same as our population distribution. So the mean of the sampling distribution is going to be 12. Straight 12, same as our population distribution. Just like the example I showed you earlier right here. Now, what is the standard deviation of our sampling distribution? So our standard deviation is going to be our original standard deviation, which let's do it on the whiteboard. So it's always going to be your standard deviation divided by the square root of your sample size. So our standard deviation was 5. Our sample size was 10. So whatever 5, and I'll use my TI-84 here. 5 divided by the square root of 10 is going to give us 1.58. So our new standard deviation for our sampling distribution is 1.58. So notice it got smaller, right? And if I increase that number from, let's say, instead of my sample size being 10, I made it 100. You're going to see our sample size, our standard deviation decrease quite a bit. So the higher your sample size, the smaller your spread, excuse me. Okay, no. So we talked about center of a sampling distribution. We talked about spread of a sampling distribution for means. Now let's talk about the shape. So if the population distribution is normally distributed, then the sampling distribution for means is also normally distributed regardless of the sample size. So you could take a sample of size 2 or a sample of size 30, doesn't matter. Your sampling distribution will always be normal if your population distribution is normal, given the 10% rule is met. If the population is not normally distributed, then we have to use the central limit theorem. And here's what the central limit theorem is. Oh, there we go. So the central limit theorem is as you increase your sample size, the sampling distribution of sample means looks more normal to the distribution and less like the population distribution. And essentially, if you draw a simple random sample of a sample size bigger than 30 from any population with an average and a standard deviation, the central limit theorem says that when n is large, and they say 30, so as long as n is bigger than 30, the sampling distribution of sample means is approximately normal. So I kind of threw a lot of words at you. Let me break that down in kind of layman's terms. Central limit theorem says as long as your sample size is bigger than 30, it doesn't matter what your population distribution is, your sampling distribution will be normal as long as your sample size is bigger than 30. Why does that matter? Well, the central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations, even when the population is not normal. So once again, it allows us to use the normal curve and the normal calculations to answer questions about sample means. And the 2007 problem that I'm going to do with you all will help answer that question or illustrate that point. Here's kind of a quick summary before we dive into some practice. We have a population with a certain average and a certain standard deviation. We take a bunch of samples and generate averages. So we take a sample, we calculate the average of that sample, throw it on our distribution. We take another sample, calculate the average, throw it in our distribution. This distribution right here will be normal if n is bigger than 30, regardless of the population distribution. If the population distribution is already normal, then we don't have to worry about how big n is. This distribution right here of sampling means the average is going to be the average of your population, and the standard deviation is going to be your original standard deviation divided by the square root of your sample size. All right, so stats is one of the classes where theory is great, understanding the theorems is great, but in order for you to really have a good understanding, we got to do some practice problems. So I'm going to go ahead and transition to our document camera, and we're going to take a look at a couple quick problems with our central limit theorem. Let me get my markers and let's dive into it. Let me move that. Okay, so it says an insurance company has found that repair claims have a mean of 525 with a standard deviation of 375. So I'm actually going to draw that distribution. And Dean, I always recommend my students draw a distribution if it's being described. So this one says the distribution is skewed to the right. So I'll make something that's right skewed. We have a mean of 525 and a standard deviation of 375. Just gives them a little context. A simple random sample of 60 repairs is recorded. What is the mean and standard deviation and shape of the distribution X? Okay, so we're going to start with the mean. Now remember, the mean of your sampling distribution is equal to the mean of your population. So in this case, my population mean is 525. So that's going to be the mean of my new distribution. Pretty straightforward. Now our standard deviation for our sampling distribution, again, the notation is important on the AP exam. If you're not writing the correct notation, they're going to dock you. And it could be the difference between an E and a P, which could be the difference between a 3 and a 4, or a 3 and a 2. So the standard deviation of our sampling distribution is equal to your original standard deviation, or your population standard deviation, divided by the square root of your sample size. So what was my original? 375. What was my sample size? 60. So we're going to go to our TI. And we're going to take 375 divided by the square root of 60. And we're going to get 48.41. Which is good because we do want something that's smaller than our original standard deviation. Right? Because as we increase our sample size, we should get a smaller standard deviation. Now, it also asks for the shape of this distribution. So shape, that's where they're getting into the central limit theorem. Right? So we would say because n is bigger than or equal to 30, on the AP exam, they will not accept just n is greater than 30. You have to actually put 60 is greater than 30. I remember one year, students didn't put 60 is greater than 30, and they actually docked students from an E to a P. So the reader doesn't assume that you know what n is. Okay? So make sure you put the actual numbers in there. And that's super important when we get to confidence intervals and hypothesis tests, when you have to check the conditions, like n times p is greater than or equal to 10, or n times 1 minus p is greater than or equal to 10. You have to write that formula and then write down what n and p are. So Dean, I know you're a little bit further than me in my class. Make sure you tell your students that they need to write down what n and what p are on their free response section of the AP exam in order to earn full credit for checking the conditions. So because our sample size is bigger than 30, 60 is bigger than 30, the central limit theorem tells us that the shape is normal. Sorry for the kind of off the side writing, but that's where central limit theorem comes into play. Because our sampling distribution is normal, and I'm going to draw our new sampling distribution. So again, we know it's normal, and this is the average of x bar. 60. Our standard deviation of x bar, 48.41. So because this is normal, we can now answer the next question, which is what is the probability that their mean repair cost for these 60 claims is greater than 610? So now they're asking us to go back to chapter 2, chapter 3, depending on your pacing, with normal calculations and z-score and all that. So they're asking, hey, what's the probability that I collect a sample of 60 that's bigger than 610? And notice I made a mistake here. Our average isn't 60. Our average is 525. Thinking sample size. So our average is 525, not 60. So we want to know what's the probability that the claim is greater than 610. And again, this is where I have my students draw it out. 2 reasons. One, it shows the reader on the AP exam that they know what they're trying to find. And it could be the difference between a P and an I if you show the reader what they're trying to find, even if you get the rest wrong. The second thing is it helps the student, it helps you all understand what you're trying to find, particularly when it comes to calculating z-score. Do I do 1 minus, or do I just do CDF? Do I do PDF? When you draw it out, it gives you a much better picture. So I'm looking for the area above 610. So I stress my students to really, really use their TIs to save time, especially on the free response when it's going to take them forever. So on the TI 84, you're going to hit second distribution. You're going to go down to normal CDF. The lower is going to be 610. The reason lower is going to be the 610 is because we want everything bigger, right? We want this and above. The upper is going to be some really, really big number. And I tell my students to put 99999999999 just to make sure that they're covering every single data point to the right of wherever we are. And I would say the same thing if they were doing something to the left. So the lower bound would just be negative 9999999, just making sure that there's no room for error. Well, our average for our sampling distribution was 525. Our standard deviation was 48.41. We're going to hit paste, and there we go. We get our answer. So the area to the right of 610, or the probability that the average repair cost for 60 claims is greater than 610, is going to be 0.0395. You could also put 0.040. AP stats, I usually tell my students to round to the third decimal spot. So if you round to the third decimal spot, you'll be fine on the AP exam. So similar, question C. What's the probability that the mean repair cost for 60 claims is in between those two numbers? So again, we're using our sampling distribution. That was really bad. With our average of 525, with our standard deviation. Again, notice how I'm writing the notation. You don't just want to put sigma. If you put sigma, you're talking about the population distribution, and you're not talking about the sampling distribution. The only way we can make this calculation is if we have a normal distribution, and we know that our population distribution is not normal. So 48.41, we want to know what's the probability. Let's see if yellow shows up. What's the probability that my claim is between, sort of, 500 and 600. So we want all this area. That's between 500 and between 600. So again, I'm going to use my sampling distribution for sample means, and I'm going to use my TI-84. Again, I really, really want you guys to be comfortable using the TI-84 because it's going to save you a lot of time on the test. If you have the Nspire, just let me know and I can quickly look up what the calculations would be for you. But to do a normal calculation, you're going to want to hit second distribution, go down to normal CDF because we want a range, not just one specific. The lower bound here is going to be 500. The upper bound here is going to be 600. Average is the same. Standard deviation is also the same. Hit paste, enter. So we found that the area inside is 0.637. Remember, I told you to round to the third decimal spot on the AP exam. You will be fine if you round to the third decimal spot. So let's go back to what the question asked. What's the probability that the mean repair cost for these 60 claims is between 500 and 600? So we're talking about the sampling distribution, not the population distribution. So we use our mean for our sampling distribution, our standard deviation for our sampling distribution, and we get our probability. Now, there are two challenge problems that I do want to go over because these are the ones that might show up on your AP exam. The straightforward ones, they might not ask, but the challenge problems, that's the ones that they're going to ask. So, challenge problems. 90% of all sample means of size 60 will be in the interval between 525 plus or minus what number? Find the value of M. So we're asking in our sampling distribution, right? It's a sampling distribution because sample means of size 60. That right there tells you it's a sampling distribution, not a population distribution. So we have our average and we have our standard deviation. Our average is 525. Standard deviation is 4841. We want to know, hey, 90% of the claims are going to be in between what two numbers? So we know that that area is going to be 0.90. We want to know how would I capture that? What would I need to go? How far out would I need to go? So to do that, we're going to use our TI-84. Second distribution, inverse norm. So remember, anytime you're giving a probability and you want to find the actual number, inverse norm is your way to go. It's going to save you a lot of time instead of going through z-score, looking up the chart. Definitely recommend getting your students and getting you guys comfortable on the TI. And if you have a question about it, just use the ask question and I'll stop and help you out. Area. So we want the middle 90%. So we put 0.9. Our average. So the average of our distribution is 525. The standard deviation. The standard deviation of our distribution is 48.41. Here's where the TI-84 really helps. You can decide, hey, what 90% do you want? Do you want the lower 90%? Do you want the center 90%? Or do you want the upper 90%? So this is where splurging for the TI-84 is really going to help you out. We want the center 90%. And there's where we get. So we get these two numbers. We get 445.373 and 604.627. So we know that the middle 90% is between 445 and 604. Now remember, this is an AP problem, so it's not going to be as straightforward. We want to know, hey, what would you need to add to 525 to get that interval? So really all we're doing is we're taking 604.627 and subtracting 525 to get about 79.627. Which should also mean 525 minus 445,373 should give us about the same 0.37. Yep, there we go. So what would we need to add to our average to cover the center 90%? 79.627. One of those will be on my students' tests. And usually when we're talking about sampling distributions, the AP exam likes to do the harder questions, so something like that will also be. As well as our next one. How would you answer part C, or how would your answer in part C change if your sampling size increased? They love to ask this question on the AP exam. So if we increased our sample size, how would it change this answer? So remember, when you increase your sampling size, for a sampling distribution, your spread decreases. So we would capture more data in the center if our spread decreased, because more of the data points on the outside are coming in. So how would your answer in part C change if your sampling size increased to 100? Well, it would increase the probability that a repair cost, a mean repair cost of 60 claims is between 500 and 600. Love to ask that type of question, and they love it so much they asked it on the second AP test ever. So here we're going to transition to our 1998 free response question number 1. So again, 1998 was the second year that the AP exam was created. The first year was 97. 98 was our second year. So here's our problem. Consider the sampling distribution of sample means obtained by a random sample from an infinite population. The population has a distribution that is highly skewed towards larger values. Well, what does it mean to have a population that's skewed towards higher values? That means it's skewed to the left. Right? That means if I were to draw it, most of my data is on the right side. Which also means, this is a good helpful hint, our median is going to be bigger than your mean. There's a little chapter 1 review for you. If something is skewed to the left, your median is bigger than your mean. If something is skewed to the right, then the opposite is true. Your mean is larger than your median. Question A, how is the mean of the sampling distribution related to the mean of the population? The same, right? So you would say something like the mean of the sampling distribution is equal to the mean of the population distribution. Now, to be honest, they're probably not going to ask something like this on a free response again, but they might ask it on a multiple choice. 98, they were still trying to get a feel of the test and how to actually assess kids' ability on the AP exam. Nowadays, on the AP exam, they like more application versus just straight, do you know the theorem? Do you know that the mean of a sampling distribution of means is equal to the population distribution? That's kind of old school AP stats thinking. New school is, hey, let's actually have them apply it. B, how is the standard deviation of the sampling distribution related to the standard deviation of the population? Again, they want a couple things here, right? We know that our standard deviation for our sampling distribution will be distribution, that's all right, will be smaller than our population. And we can actually tell you exactly how much smaller, right? It will be divided by the square root of n smaller. And just for good measure, we also might want to note, as you increase n, the standard deviation for your sampling distribution will decrease. Again, probably not going to be asked on the free response part, but will probably be asked on the multiple choice part. Well, not probably, right? We don't know what they're going to write. Although I do have a friend who does write the exam questions. Unfortunately, he cannot tell me what was on there. C, how is the shape of the sampling distribution affected by the sample size? All right, so here they're looking for that central limit theorem, right? We talked about the central limit theorem, so if you didn't quite catch that, go ahead and watch the replay and catch our activity around sampling or central limit theorem. So here they're looking for something along the lines of, and I'll just read you straight from what they're asking. The shape of the sampling distribution gets more and more normal as the sample size increases. And since the population is skewed, if we take sample sizes less than 30, our sampling distribution will also be somewhat skewed. Until we hit that 30 mark, then it'll become more normal. So the sampling distribution is skewed for all small sample sizes, but as you increase your sample size, the sampling distribution becomes more normal. All right, so that's straight central limit theorem. Again, they probably won't ask that on a free response. They'll probably ask that on a multiple choice. All right, so let's do a more recent AP problem. One from 2007. And let's dive into it. So these frappies are great for students. Highly recommend you give them out to them so that they can practice the AP exam questions as well. So it says, big town fisheries recently stocked a new lake in a city park with 2,000 fish of different sizes. The distribution of lengths of these fish is approximately normal. Super important. So we know that our population distribution is normal. Good to know. I am going to draw it out. A, Big Town Fishery claims that the mean length of fish is 8 inches. So they're saying, hey, with all these fish in the lake, our average is going to be 8 inches. If the claim is true, which of the following would be more likely? A random sample of 15 fish having a mean length greater than 10 inches, or a random sample of 50 fish having a mean length greater than 10 inches. All right, we increased our sample size. What happens when you increase your sample size? Your spread decreases, right? So let me draw it out for you. If we had our sampling distribution, let's say our first one is, let's say the first one is the 50. So this is n equals 15, I'm sorry. Then we have a new sampling distribution for the 50. So your centers are going to be the same, right? Our centers are going to be the same. It's going to be centered around 8 inches. What's going to be different is your standard deviation, right? So the standard, let me write, that is n is equal to 50. Your standard deviations are going to be different. The standard deviation for the 15 is going to be whatever your standard deviation is divided by the square root of 15. Your standard deviation for the 50 is going to be whatever the population standard deviation is divided by the square root of 50. So because that's going to be a larger number, when we divide it into our population standard deviation, we're going to get a smaller number. So that's important to know, right? So it will be, so which of the following will be more likely? A random sample of fish having a mean length greater than 10, or a random sample of 50 fish having a mean length greater than 10? Well, it's going to be this one, right? It'll be much easier to take a sample that is of 15 fish that have a bigger length than 10 than it will be 15 or 50, because 50 we can pull from all sorts, and it's just going to decrease our sample size. So essentially we're saying, hey, let's say this is 10 inches right here, which is going to have a bigger probability, this little part here or this whole part here, right? That's going to be more likely because this is a smaller area. All right, let's go to B. I got 13% on my battery. I'm hoping to make it last. If not, I might pop out, grab my charger. Oh, wait, just kidding. My charger's right here. There we go. Okay, let's dive back into it. B, suppose the standard deviation of the sampling distribution of the sample mean of a random sample of size 50 is 0.3. Great, we have new information. So they're saying, hey, remember your distribution for 50? We know what that standard deviation is. It's 0.3. So we now know that our standard deviation for X bar when we have 50 fish is 0.3. Again, your notation matters on the AP exam. If you just wrote sigma, that would indicate to the reader that you're talking about the population standard deviation. And we are not talking about the population standard deviation. We are talking about the sampling distribution, that standard deviation. If the mean length of fish is 8, use the normal distribution to compute the probability that a randomly selected sample of 50 fish will have a mean length less than 7.5 inches. All right, so we know this. Let's draw it out. We have our normal curve. We have our average is 8. We have our standard deviation is 0.3. We want to know what's the probability that when we sample 50 fish, the average is less than 7.5. Again, this is where drawing it out really helps. So 7.5, we want to know what's the probability that it's less than. Now we could use z-score and go through all that. Again, to save time, use your calculator. It's going to save you a whole bunch of time. If you're not comfortable with it, please let us know on the Fiveable page so I can have a session dedicated just for calculator stuff. And we'll have that towards the end of the year, but you're going to want to get that done now. So, second VARs, normal CDF, lower bound. Notice that lower is like all the way down here. So we're going to use negative 9999999. Upper bound, 7.5. Average, 8. Standard deviation, 0.3. We're good to go. If you're using the TI-83, you have your parentheses. You're just going to do those numbers in order with a comma. So it would be negative 9999, comma, 7.5, comma, 8, comma, 0.3. Close your parentheses. There you go. So the probability, and this is where I would write it out. Let's do that. So the probability that my sample is less than 7.5 is going to be about 0.048. Okay. All right. Let's dive into C. Suppose the distribution of fish length is in the lake was not normal, but had the same mean and standard deviation. Would it still be appropriate to use the normal distribution to compute the probability in part B? Justify your answer. Central limit theorem all over, right? So again, suppose the distribution of fish lengths in the lake was non-normal. So this that we had up here when it said it was normal, they're saying, hey, what if it's not normal? Would it still be appropriate to use the normal distribution to calculate the probability in part B? So would it still be okay to do this if our population was not normal? The answer is yes. Why? Because the central limit theorem says that sampling distributions, I'm just going to put distributions of X bars will become approximately normal as n increases. Since n is equal to 50, or n is larger than 30, we can say our sampling distribution will be normal, or will be approximately normal. I'll just leave it like that. So interesting to compare 98 and 2007, right? They kind of touch on the same stuff, but you can see how in 2007, they're asking you to apply the central limit theorem. And in 1998, they just asked you, like, what is the central limit theorem? So we're coming into an age of statistics where the AP exam is asking for more application. Even though this was, 12 years ago now. Wow, 12 years ago. That will get you a 4 on this exam. and it won't take you too long. This is where you would want to bank some of your responses. Coming up on an hour. Sorry we went a little long, but this is a very, very important topic to dive into. So I'll stick around for a little bit. If you have any questions, go ahead and ask the question. Once again, if you enjoyed this video, please share with your students, share with your colleagues, share with your fellow peers, anyone who you think could benefit from these live sessions. These live sessions are free now, which I'm really, really happy about. And you can get Fiveable Plus on 55% off this week up until April 1st, I believe. I'll double check that. Which you can get replays, you'll get cram sessions, you'll get any kind of activities that we do. You can get that all for Fiveable Plus. Looking forward to continuing our journey together. It's getting towards crunch time, so please make sure you're putting in the time studying, you're asking your teacher questions, you're doing the readings, you're doing the homeworks, and you're seeing me every Thursday for an hour. Hour a day, hour every week with me will definitely help you improve and hopefully save you a couple $1,000s in college. Also, I know I said this earlier in the year, but statistics is one of those. Anytime, Dean, really appreciate you having on here. Email me with any questions or any resources that you want. Statistics is one of those courses that you're gonna see again in college regardless of what you do. It's a really powerful course, and I hope you feel the same way I do. And I will see you all next week.